Alright, hey there you guys, welcome back to the Calculus Fun Room. In this video what I want to discuss with you is the precise definition of a limit. This is sometimes called the epsilon delta definition of a limit. Now in a prior video we discussed doing limits using limit laws. I sometimes call them shortcuts because they make evaluating limits relatively efficient. What we want to do in this video is look more general. So we want to look at arbitrary values and how close we can get to a particular value of a function. So just to remind ourselves of what we're looking at in regards to a limit value. Let's suppose we have the piecewise function f of x equals, and we'll say f of x equals 2x minus 1 if x is not equal to 3. And then we're going to say, let's suppose f of x equals I don't know, let's say we have f of x equals negative 1 if x equals 3. So visually, right, if we sketch this graph real quick, let's just look visually here. So if I'm plotting the line 2x minus 1, right, this is a y-intercept of negative 1, so let's plot that value, and then it's a slope of 2. So I would rise 2 and go over 1. There's a point there. And then I would rise 2 and go over 1, so let's say roughly there's a point there, right? And then if I go out to x equals 3, I would rise 2 more to 5 and then go over the 1 value, let's say roughly there's that point, right? So here's our line roughly 2x minus 1, and then when we get to x equals 3, the y value is negative 1. So here's my y value when I get to 3. Now, because x cannot equal 3 on my line, let me come back up here and put an open hole to define that x is not equal to 3 on the line 2x minus 1. Now, let's suppose we were looking at the limit of f as x approaches 3. This limit means we're going to get closer and closer to 3 without actually getting to 3. So if I come over here on my graph again, look visually, as I get close to 3 from the right, we can see the y values are trying to get to 5. And as I approach 3 from the left, we can see the y values are trying to get to 5 as well. All right, now again, within the limit process, we're not letting x equal 3, right? If we let x equals 3, the y value is negative 1. But we're getting closer and closer to 3, and our y value is 5. So in the prior section, we would just plug 3 in to the equation, and we would see, 6 minus 1 equals 5. That's our limit value for this particular example. Now, remember symbolically what we typically would write is we'd say the limit of any function f of x as x approaches a equals L. So for this particular example, our a value is 3, our L value is 5. That's our limit notation there. So what we want to do in this section is we want to look in an arbitrary manner, right? So we're basically asking how close do I need to get to x equals 3 so that I'm getting close to y equals 5. Let's say we want to ask how close to 3 does x have to be so that, let's say, the y values, right, f of x, differs by less than let's say 0.1. Okay, so pause the video real quick just to fix my sentence, right? So how close to 3 does x have to be so that the y value, right, my output, differs from 5 by less than, let's say, 0.1. So this is my tolerance. I want to be within 0.1 units of the number 5, and I want to find out how close to 3 do I have to be to make that work. So we're talking about distances basically, right? Like how close to 3 do we have to be? How far away from 3 do we have to be? And if we think distances in general, right? I mean, if I'm looking at a number line and I'm at the number 3, let's say I move out to the number 4, right? What's the distance that I am away from 3? So my distance, we always do like 4 minus 3, right? That's my distance. And we usually use absolute value. I want to say we don't usually. We always use absolute value. So 4 is a distance 1 away from 3. And here's that distance on that number line, right? And even if I move down to 2, what I would typically say in that case is 2 minus 3. Now granted, 2 minus 3 would be negative 1, so we use absolute value. So the distance that 2 is from 3 is 2 minus 3. Now what we want in this case is to ask, what is that value in an arbitrary manner? So instead of picking specific values here, what I'm going to do in that case is I'm going to pick 3, and let's say I want to move out here to some number, let's call it 3 plus. What we typically use in this type of section is the Greek lowercase delta. So we'll use delta to represent some distance, right? So we've moved some distance away of delta, right? That's our distance. Right? I drew the number 2. Let me fix that to be delta. Right? So in other words, we want to have x minus 3 to be less than delta. In other words, we want this number to be some x value. So we're going from 3 out to x, and the distance from 3 to this x value is x minus 3. So just like we talked about here, the distance 4 is away from 3 is 4 minus 3. The distance that x is away from 3 is x minus 3. So we're looking for that distance to be some number delta. We want to find that number. And we want that number to be true so that we're within the y value, right, of a distance of 0.1. So this was the question we asked, right? We want the y value to be a distance of 0.1 or less. So we want to be within 0.1 of my limiting value. And we want to find how far from x equals 3 do we need to make that work. So we don't know what this distance is, and what we're asking here is, what does that distance need to be so that my tolerance is 0.1? So how do we find this number delta? How do we find how close we have to be so that we're within 0.1? All right, if we come back and look at our graph real quick, or visually, what are we talking about? So visually, let me pick the color gray that I want to draw with here. Visually, you want to be, let's say, within 0.1 units of the number 5. So I have basically, 4.9 is what I want to look at, and 5.1. So I want to be within 0.1 units of the number 5. And so what I'm really asking for is, what does this x value need to be, right? How close, what's my delta that will make that work? How close do I need to be? And then again, ditto here, how close do I need to be, right? What's that delta that we're talking about here? My graph's a little cluttered, right? But here's a value of delta. So how close to 3 do I need to get so that my y value is within 0.1 of 5? All right, so let's take a look at this expression here for just a moment. So again, we want to be within 0.1 of our limit value of 5. Right? So we want the y value to be a distance of 5 that's less than 0.1. That was what we're drawing visually here. And I'm going to replace the f of x with the equation that we had up at the top of our notes. So we have the graph 2x minus 1 when we're close to 3. And we want its distance from 5 to be less than 0.1. So if I plug the f of x in here, let's do a little bit of algebra with this. And let's notice that this becomes 2x minus 1 minus 5, which is minus 6. And then I could factor a 2 out of this. So if I take a 2 out, I get 2 times x minus 3 is less than 0.1. And then I'm going to divide both sides by 2. So I get x minus 3 is less than 0.1 over 2. Now, if we come back up here and look at our definition, right, or our question, right? So if we're going to satisfy this expression, right, that the y value is 0.1 distance from 5, then x minus 3 has to be less than some number delta, right? How close do we need to get that number delta that we had here? And by plugging the f of x in and doing a little algebra simplification, we can see that x minus 3 would be less than 0.1 over 2. So we have, in essence, through a little bit of algebra, found what that found what that delta needs to be. The delta needs to be 0.1 over 2. All right, now the concept in this section is I don't want to do these limits for any specific tolerance. So we picked a specific tolerance of 0.1, but I want 0.1 to be anything that it can be, right? So in other words, I want to get as close to 5 as I can. So what if I ask the question and I'm within 0.01 of the number 5, right? What would the delta be? How close to 3 do I need to get so that the y value is within 0.01? Well, if we just kind of look at this algebra, if we continued with this process, I would end up with 0.01 over 2. So if I want to be within a tolerance of 0.01, then I need to get 0.01 over 2 distance from the x value. And if I make this 0.001, so if I get even closer to the y value of 5 and make this distance 0.001, then I'm going to need the x value to be 0.001 over 2 in order to make that work. So again, I want this to be arbitrary. I don't want to pick those 3 or 4 tolerances. I don't want to pick specifically 0.1 or 0.01 or 0.001. I want this to be any arbitrary distance from the value 5. So the way we typically write this is in the following manner. So we want the function value f of x to be any distance from 5. And we're going to call that some positive number epsilon. And we want this y value, right, to be a distance of 5, any value that we choose, and we're going to have to choose the x value to be some distance delta for any value epsilon and delta. So these are our arbitrary values. Now in this particular case, we found out that if we choose some number epsilon, that the delta would be epsilon over 2. So for this specific example, right, let's say for, f of x equals 2x minus 1 or negative 1. So for this particular example, the limit, right, of f of x as x approaches 3 will equal 5, right, is defined in the following manner. We'll say that basically this is true if for any positive epsilon and delta that f of x minus 5 will be less than epsilon if x minus 3 is less than epsilon over 2. That was our delta value. So in a very arbitrary fashion, we're saying we can get as close to 5 as we want as long as we are this close to the x value. All right, so again, visually, I'm a visual learner, so I'm going to look at this visually, right? When we had drawn this graph a couple minutes ago, and we said, here is the graph 2x minus 1, and we had an open hole here. So at x equals 3, we were approaching 5. Right, so again, we want, in essence, this to be 5 minus epsilon, and this to be 5 plus epsilon. So we want epsilon to be arbitrary. And we're asking, in order to make that work, we want to look at this number, 3 plus delta, right? And in order for this distance to work, we're looking at 3 minus delta. So in order to get within a distance epsilon of the number 5, we just found out that the delta needs to be epsilon over 2. Now, again, for this particular example, this is the relationship that works. And that's not always the relationship. Sometimes this delta will be something different. And what it really depends upon is the function that we're looking at. So the purpose of this section is to discuss how could we determine the epsilon and delta relationship for any function f of x. Okay, so let's take a look at this in an arbitrary manner, because the point of this section is that we want to prove limits based on how close we can get to each number. So here would be the official definition. So what we basically say is, let's let f be a function defined on an interval that contains x equals a, except possibly at x equals a. Right? So again, we don't need the function to be defined at x equals a because we're getting close to a. So we can officially say that the limit of f of x equals some number L as x approaches a if for every possible epsilon there exists some delta such that we will be within the distance epsilon from the limit L as long as we can get within a distance delta from the value a. All right, so just to illustrate this concept a little bit more, all right, let's do another example together. So let's suppose we have a problem that says something like we want to prove that let's say the limit as x approaches 3 of the function 4x minus 5 is going to equal 7. Let me stress the limit we're looking at. Right, so here's the function 4x minus 5, and we're letting x approach 3. And again, we know by direct substitution that if I plug 3 in here, 4 times 3 is 12, 12 minus 5 is 7. And the reason we can just plug 3 in is this linear function is continuous at x equals 3 or near x equals 3. Now, what we're wanting to do in this section is use the epsilon delta definition to prove that this is true as we get arbitrarily close to 7, right? So how close do we need to get to 7, right? So if we want to get infinitely close to 7, how close do we need to get to 3 to make that work? Right, so again, visually, what we're looking at here, I'm a visual learner, I got to sketch this graph. We have a line where the y-intercept is -5, let's say down here somewhere, and the slope is 4, so it's positive, we know it's increasing, looks something like this. So we know that when we get to 3 through direct substitution, this y value is 7. So again, we're discussing the idea that we want to be some distance from 7, and we're calling that the number epsilon. So we're moving the distance epsilon above and below 7. And I want to ask myself that when I do that, how close to 3 do I need to get? And we called that distance delta. So I want to move a distance delta above, and I want to move a distance delta below to make that work. And we want to find for any arbitrary epsilon, what's the delta that makes this closeness work. Right, and again, in the prior example, we picked a specific epsilon value, right? So in the prior example, we picked a tolerance of 0.1. So we said we wanted to be 0.1 above, 0.1 below. And we asked how close to this x value do we need to get to make that work. And we found out that 0.1 divided by 2 is what made that work. And so we generalized and figured the relationship down here was we had to get within epsilon over 2 to make that work. So I don't want to pick specific numbers for epsilon anymore. I want to do this in an arbitrary manner. All right, so in order to do an official proof, what I want to do is do some exploration. So before we even really begin the proof, we're going to explore to see what relationship we might have in this case. So remember that what we want is f of x minus 5 to be less than epsilon. For any epsilon, excuse me, this is 7. My limit is 7. Let me fix that. So we want the distance from 7 to be some positive epsilon number. So for this particular example, f of x is 4x minus 5. So let's plug in 4x minus 5. So we're asking how far from 7 does my function 4x minus 5 have to be, right? So if I simplify this expression, I get 4x minus 12 has to be less than epsilon. I can factor a 4 out of here, and I end up getting 4 times x minus 3 is less than epsilon. Now remember, we want this to be true when we have x minus 3 less than delta, right? Visually, come back over here again, right? We want a distance of delta from the number 3. So we want my distance, x minus 3, to be less than delta. And I can see right here, here's x minus 3. So if I divide the 4 over, then we're seeing that the distance we need to be, I'm dividing by 4, we can see that the distance we need to be from the x value is epsilon over 4. Now this is an exploration to see if we can find the relationship between epsilon and delta. What we need to do in this case is now prove it specifically in an arbitrary manner. So instead of an exploration, we're going to now come back to this process and we're going to prove for any arbitrary epsilon and delta that the definition holds. All right, so let's do the official proof in this case. So again, based on our epsilon delta definition, right, in order to prove that this is true, right, what we're looking for is we need, let's say for any positive epsilon, right, we need to find a delta that makes the definition true. So we basically say there exists positive delta such that if the distance of x from 3 is less than delta, then we can get arbitrarily close to 7 for my function values. So what we'll do in the proof in this case is we'll say let's choose delta to be epsilon over 4. So if x minus 3 is less than delta, so we're going to kind of work backwards here. We're going to say if x minus 3 is less than delta, then we're going to write f of x minus 7 is equal to, and we're going to do the factoring that we did before. I'm going to say 4x minus 7, excuse me, my function is 4x minus 5. And we're going to say 4x minus 5 is a distance of 7. And then we're going to simplify this expression here. I'm going to say 4x minus 12. And then we're going to factor the 4 out. And what we're going to point out to ourselves in this case is that x minus 3 was less than delta, right? So we want this to be true. So x minus 3 is less than delta. So if I replace x minus 3 with delta, then 4 times x minus 3 is going to be less than 4 times delta, right? So I'm just replacing x minus 3 with the delta that we're looking for. Now we chose delta to be epsilon over 4. So this is equal to 4 times epsilon over 4, which simplifies to just epsilon. And then we have satisfied that definition. Okay? So in other words, we have x minus 3 being less than some arbitrary distance delta, then the f of x minus 7 will be within some arbitrary distance epsilon. All right, so then we summarize this so that we show we have satisfied the definition. So we say thus, right, this is a summary, therefore, if x minus 3 is within some arbitrary distance of delta, then we have just shown that the f of x is some arbitrary distance epsilon from 7. Right? So by definition, we have proven of the limit, of a definition of the limit. We know that for x minus 5 will be equal to 7 as we get close to 3. So this is the formal proof based on the definition of the limit. All right, let's go ahead then and do one last example where we are proving a particular limit. So for this example, all right, let's suppose we want to prove that, let's say, the limit of square root of x as x approaches 0 from the right is going to equal 0. Right? And again, through direct substitution, we could just plug 0 in and see that we're going to get 0. But what we want to do is prove that we can get arbitrarily close to 0 as x approaches 0, right? So kind of like in that very first example, right? How close to 0 do we need to get so that our y value is close to 0? Well, just like in the last example, what we did was we did a little bit of exploration, right? So let me go ahead and, just kind of explore. And remember, the purpose of this exploration is we're finding values of delta. So I want to explore the relationship of delta and L, right? Of epsilon, sorry. What's the relationship between delta and epsilon? In general, right, we look at x minus a is less than delta when f of x minus L is less than epsilon, right? That's our definition. For this particular example, our x value is approaching 0, right? So we're looking at x minus 0, right, is less than delta, right? That's the value that we want. And again, our limit here is 0 as well, so we have minus 0, right, and that being less than epsilon. Now in this case, our f of x, right, so we're looking at our f of x. Let me squeeze over here just to have a little extra space. Our f of x is root x, and we want that to be less than epsilon. Now keep in mind, the things that come out of the root are positive, right? This is our principal root. So I don't really need the absolute values in this case, right? And then to quote-unquote solve for x, I'm going to square both sides, and we get this value. Right? So visually, right, well, not visually, right, let me look at the equations in this case. We can see that for x to be less than delta, we need x to be less than epsilon squared. So what we're going to do then in this case is we're going to choose our delta to be epsilon squared in order to make our proof work properly. Okay, so now the proof, right, is that what we're really doing, we're showing this delta works, right? We're going to show that that delta works appropriately. So again, we're going to say, given some positive epsilon and delta, what we're going to do is choose, right? We're going to let delta equal epsilon squared. So what we saw prior, right, was that if x is between 0 and delta, right, this is my x minus 0 being less than delta. So we're going to square root both sides here and get square root of x is less than the square root of delta. And then we know that delta is epsilon squared. So this guy right here, I'm going to replace with epsilon squared. So I have the square root of x being less than epsilon squared. So square root of x, is less than epsilon. Now remember, square root of x being less than epsilon, this is my f of x, right, minus 0. So this guy is my f of x, right, minus 0 being less than epsilon. So we have proven that if x is less than delta, where delta is epsilon squared, then my f of x is less than epsilon. Right? So by definition, we have proven that the limit of square root of x as x approaches 0 from the right will equal 0. Okay, I think that's all the examples I want to do here where we have discussed the epsilon delta definition, where we're going to prove that we can get arbitrarily close to the limit L as we get arbitrarily close to the value of x.